Okay, welcome to Physics 223. We are Mobius 4. We're going to demonstrate for you our superconductor track. Here we have our track almost assembled. There's several things that we wanted to show you before we actually assemble the track and actually show you what properties superconductors actually possess. First of all, we want to talk about, actually show you a demonstration of what the Meissner effect is, what one of our colleagues actually had previously talked about in our live presentation. We're actually demonstrating this for you by videotape because of the cautionary procedures that we have to take into account because of our liquid nitrogen here. So not everybody can have safety goggles in our classroom, so we're actually videotaping this for you today. As we discussed before, a superconductor is a type of material that when we actually cool it down past its critical temperature, roughly about 180 degrees below zero, we're actually going to have the superconductor itself will lose all of its electrical resistance. And so what we'll do now is we'll demonstrate the Meissner effect for you. We're going to grab some liquid nitrogen and we'll be right back. So what Jesse's doing right now is pouring the liquid nitrogen in there to actually cool down the superconductor material past its critical temperature, as we mentioned before. I'm actually going to get a permanent magnet and place that over the superconductor to kind of show you the Meissner effect. So when this is still cooling down, and as you can see now, if we can go ahead and zoom in if you can. If you can see, this is actually locked into position. The superconductor has actually created a magnetic field. Basically, and this permanent magnet here is locked in position. I can actually remove it and actually place it back over the superconductor, and you can see I can actually turn it, I can spin it. Oh, and there it is again. So even dropping it, it stops because it locks into this magnetic field that the superconductor has actually created. Okay, we're back now. We're going to actually demonstrate quantum levitation using our super strong neodymium track and a type of ceramic material. It's called yttrium barium copper oxide, or YBCO. It's a type 2 superconductor material here. We're actually just going to cool this down again like we did before, but we're going to place this over the track when it cools so that it can actually lock into position. We have our very expensive liquid nitrogen holder here. So as you can see, it's actually cooling down here. When the superconductor has actually reached its critical temperature, even past that, it's actually going to start levitating in this kind of polystyrene tray here. And we're using polystyrene actually because it's a very good insulator. All right, so it's actually locked into position. This is going to be very challenging here to get this. As you can see, as I move this tray, the superconductor is locked into position over the track.
Is it going to work? Okay, good.
So as you can see, this is actually levitating. Oh, it actually stopped. So unfortunately, it warmed up very quickly because the room temperature and other factors. And of course, when it warms up very quickly, it loses its superconductive properties. So in order to explain that, we're going to take you live into the classroom and actually explain basically what electromagnetism is all about. Okay, welcome back to our demonstration. As you recall, the superconductor itself warmed up very quickly and lost its superconductive properties because it warmed up. So to try and combat that or fix that issue, we actually created a reservoir with polystyrene. The superconductor itself, as you can see, is embedded in the bottom of the polystyrene. And there's a reservoir here where we can put the the liquid nitrogen, to actually cool off the superconductor, but keep it cool for a longer period of time. As you remember, it was about 10 seconds that we demonstrated its properties over this track. But now we're going to do it with this and see how it works. We're actually going to cap this. To sort of seal in all that coolness and prevent it from warming up too quickly. So as you can see, this is actually locked into position. And there's actually nothing underneath here. And as so like any experiment, you try and try again until you get it right. Okay, I think it's locked into position. I'm going to remove it from this tray. Not quite yet. And I think something's wrong. Yeah, we got to redo that. So like any experiment, you try and try again until you get it right.
Should be, I guess.
It's best. So you see, it has to be cooled.
Yeah.
So we have to wait until it warms back up.
Okay. Sorry.
So that was the issue. This was already too cold when we got it up there to begin with. And so as you can see, it was tilted, so it wasn't flat. And so it needs to be flat. And so when we tilted this, it actually came off. So like any experiment, you try and try again until you get it right. So let's stop that right there. So what's going on is the magnets are not repelling the superconductor. As we discussed earlier with the copper conductor in class, the electrical fields which are induced by moving magnetic fields or changing magnetic flux, they themselves have magnetic fields which are arranged in such a fashion so as to resist the motion causing them. In this example, gravity is causing the superconductor to move towards the track. That motion sets up an electrical field in the superconductor to resist that motion. Likewise, as the track is turned to 90 degrees, or even as it is inverted, gravity is now pulling it away from the track. This propensity to want to fall away sets up new electromagnetic fields to cause the superconductor to remain in its current three-dimensional position relative to the track. So no matter what orientation the conductor finds itself at, whether that be above, to the side, or below the track, the electrical fields induced will always arrange themselves as at those moments so that the only position the superconductor wants to or is inclined to move is where the magnetic fields themselves are not changing, that is along the track. Okay, we're going to try this again. So like any experiment, you try and try again until you get it right.